Right now, every second of your life, an invisible substance is passing straight through your body. As we zoom out from our solar system and plunge into this pitch-black, empty void, we are entering the space where this untouchable material is supposed to live. We know it exists because we can observe its gravity. Look closely at this dense field of galaxy clusters. We can watch invisible mass bending the light of these distant galaxies into glowing arcs. We can see it holding rapidly spinning galaxies together, when by every law of physics we understand, they should be flying apart. By the best measurements we have, this unseen stuff outweighs everything we can see, every star, planet, and cloud of gas, by more than 5 to 1. Roughly 85% of all the mass in the cosmos is simply missing from our view. We call it dark matter, but that name is mostly a confession of our ignorance. Astrophysics now grapples with a paradox. A substance that makes up the majority of reality has managed to evade every attempt at capture. For decades, physicists thought they knew where to look: the WIMP, or weakly interacting massive particle. The math suggested a heavy, sluggish particle that ignores ordinary matter, until chance causes it to bump an atomic nucleus and give itself away with a tiny flash. The math was elegant, but capturing that microscopic spark presented a massive engineering problem. The surface of the Earth is constantly hammered by a dense, deafening rain of cosmic background radiation that washes out any delicate signals. To hear a WIMP, scientists had to isolate a detector from all that noise. This historical photograph shows a mining complex in South Dakota. Almost a mile beneath those black hills, carved out of this old gold mine, sits the LUX-ZEPLIN experiment, or LZ. It is 10 tons of ultra-pure liquid xenon, shielded by 1,000 meters of solid rock, to block out the cosmic rain and create a silence that rarely exists on Earth. To understand LZ, you must appreciate the obsession that goes into that silence. Picture a single microphone placed at the bottom of the deepest, quietest well on the planet, waiting years for one specific whisper. The LZ experiment operates at an extreme level of precision, improving upon the instruments of the 1990s by a factor of 3 million. It gathered data for 417 days, forming the largest data set ever collected by a dark matter detector. And in that pristine silence, they found no WIMPs. None. The signal they had built this entire cathedral to hear simply was not there. One empty detector could be a fluke, but deep beneath a mountain in central Italy, a separate tank of xenon called XENONnT ran a blind analysis. The team deliberately hid the answer from themselves to prevent any bias. When they finally looked, the result was the same: no significant excess, just the same ringing silence. Two of the most advanced instruments humanity has ever engineered, on 2 different continents, told the exact same story. We looked harder than ever before and found that the most elegant theories in physics now face a difficult reality. But the detector wasn't actually empty. Buried inside the LZ data was a signal no dark matter experiment had ever captured before. Look at the active surface of our own sun. The detector had caught neutrinos, ghostly, nearly massless particles forged in the solar core, slipping through that mile of rock as if it were not there. Catching the sun revealed a problem for the hunt. This side-by-side comparison shows why. When a solar neutrino bumps a xenon nucleus on the right, the flash is the mathematical twin of a WIMP collision on the left. This is the neutrino fog. As we scale out, you can see how building a more sensitive detector only gathers thicker layers of solar noise. The background hum of the universe begins to drown out the signal we want, shrinking the returns on new data to almost nothing. We did not hit a wall someone built. We hit the edge of what nature will allow us to observe with these tools. We have pushed our instruments so far that the universe itself has started whispering back, in a voice that sounds like the one we are straining to hear. You might expect an empty tank to feel like defeat, but in science, finding nothing is a distinct way of learning. This block represents the parameter space, every configuration dark matter could take. Every empty detector acts like a sculptor's chisel. Each result erases vast regions of incorrect possibilities, slowly revealing the shape of what must remain. The WIMP has not been proven impossible, but the comfortable, elegant version of it, the one we hoped for, is being squeezed into smaller and smaller corners of the map. This patient accumulation of data performs a precise interrogation of reality. Every empty result is a surgical narrowing of the unknown that forces researchers to clear away the dead ends. As the search for heavy particles hits these limits, a different candidate has stepped into the spotlight: the axion. It is almost the opposite of a WIMP. The axion is nearly massless, perhaps trillions of times lighter than an electron. You can't catch a particle that light by waiting for it to bump into a nucleus. Instead, physicists build supercooled magnetic receivers, essentially turning a dial and sweeping for one impossibly faint radio frequency hidden in the static. Most of science looks like this: patient, disciplined searching, and a long succession of careful no's. This dense field of stars is a reminder that mapping the boundaries of the unknown is as vital to progress as the final discovery. 85% of the matter around us is still silent, slipping through everything we build to catch it. That sometimes the most profound thing the universe can offer us is nothing at all, because that silence is what pushes us to ask a better question.